To take pictures of exoplanets in our galaxy, we would need very large telescopes. Even for the closest exoplanets, the telescope needed to get an interesting image would be extremely difficult or even impossible to build. But there is a way that could allow us to image even distant exoplanets. We could use the Sun as a huge lens. This concept is called solar gravitational lensing. The light trajectory of an exoplanet passing the Sun gets bended due to the Sun's gravitational field. In contrast to an optical lens, the light rays get collected in a focal line instead of a focal point. To understand the behavior of the light rays, we want to find an expression for the time a light ray needs to get from the source, in this case from the exoplanet, to the position of the observer. To start, we will use this equation that was already found for usual gravitational lensing. Our goal is to derive an expression for the amount of light that arrives in the observer plane, and we want this expression to depend on small r. Using the tangent function, we can replace theta I by the arctangent of capital R, the distance of the light ray from the center of the Sun over the distance dsl between the exoplanet and the Sun. In reality, the distance dsl will be a very large distance compared to r, so the angle theta I is very small. Therefore, we can even say theta I is approximately r over dsl. In the same way, we replace theta s by the arctangent of small r, the distance of the light ray from the center of the observer plane, over the distance dso between the exoplanet and the observer. And again, theta s will be a very small angle, so we can say that theta s is approximately small r over dso. Replacing theta I and theta s in the first expression and doing some algebra, we finally get an expression that depends on small r and the direction angle of small r, small phi, and on capital R and the direction angle of capital R, capital phi. Let's try to understand better why this form of the arrival time equation is useful. With this arrival time equation, we already have a lot of information about the behavior of the light in the observer plane and in the solar plane. For example, for a specific value of small r, let's say 2 times 10 to the power of 8 meters, we can plot the arrival time of the light in the solar plane as a function of capital R. The arrival time of the light is closely connected to the phase of the light, so in this plot we can actually see the phase change of the light. In the white ring region, the phase change is very slow, and in the regions inside and outside the white ring, the phase changes faster. The ring where the phase changes slowly is called Einstein ring, and you may have already seen this Einstein ring in pictures like this one imaged from the Hubble Space Telescope. Only the region of the Einstein ring is visible, because in the outer and inner part, where the phase changes quickly, the light cancels out by destructive interference. Our next step is to use the arrival time equation to derive the intensity of the exoplanet's radiation in the observer plane as a function of small r. Now we will look at the calculation steps needed, but we will go through them rather hurriedly. To get the amplitude in the observer plane, we need to sum up all the light coming from the solar plane. So the amplitude in the observer plane is given by the exponential function of 2 pi I nu multiplied by the arrival time integrated over the solar plane. Doing some algebra, we can replace the angular part of the integral by a Bessel function of order 0. The phase function of the light is now the real exponent in the exponential function. In order to simplify our calculations, we can approximate the phase function with a Taylor approximation around the region of minimal phase change. RE is the distance of the region with the minimal phase change, or in other words, the distance of the Einstein ring from the center of the Sun. Inserting the approximated phase gives us the new amplitude function, and since the intensity is the amplitude squared, we also found the intensity as a function of small r. With this intensity equation, we find the point spread function of the light in the observer plane. We can also derive a formula for the amplification of the light due to the solar gravity lens. The amplification factor μ is the absolute value of the intensity function we have already seen, divided by the intensity I0 of R that we would measure without using the Sun as gravitational lens. The only difference between the two intensity formulas is that Re is equal to 0 in the equation of I0. This is the case because without using the Sun as gravitational lens, we don't have an Einstein ring, or in other words, the distance from the center to the Einstein ring is 0. With some algebra, we finally get a formula for the amplification factor of the light. The formula we found is by a factor 2 larger than the formula that was found by Turyshev and Toth using Maxwell equations. And so far, we have no explanation for this difference of a factor 2. Now we will look at some examples for objects that could be possibly imaged with solar gravitational lensing. Let's look at a fictional exoplanet similar to our Earth at a distance of 10 light years and at a measure point in the focal region at 600 astronomical units. Could we observe such a planet? Or could we possibly even see the university campus Irchel that has a size of about 500 times 500 meters on the planet? Let's assume the campus Irchel is the only object on the planet that reflects its host star's light. We need to consider that we always have disturbing light from other sources. The brightness of the sun, for example, but this one we can block out with a coronagraph. But there still is the background brightness from the light of all the objects in the universe, which is impossible to block out. Summing up the background over the Einstein ring, we get a total background brightness of 200 photons per meter square per second. And in reality, all the surroundings of the campus would also radiate and disturb our image. But for this example, we will ignore that. The amplified flux that arrives from campus Irchel is as well about 200 photons per meter square per second. That means with a long enough but feasible exposure time, it is possible to measure the radiation of campus Irchel. And we also find that the minimal measurable distance on the exoplanet is about 50 meters. So in the perfect circumstances we assumed, we could even image campus Irchel with about 100 pixels. As next example, we take the closest known neutron star, which is at a distance of 457 light years. The amplified photon flux that arrives from the neutron star is about 1.4 times 10 to the 13 photons per meter square per second, which is much higher than the background brightness, so this could easily be measured. And due to the rather high frequency the neutron star emits, the minimal measurable distance is even 9 meters. For the next example, let's consider an intelligent species living on a planet at a distance of 10 light years would try to communicate with us using laser signals. Would we be able to receive their message? Let's assume they use a laser with a wavelength of about 1 micron that produces about 1 kilowatt. We assume the beam diameter at the origin is 1 centimeter. To calculate the half angle of the beam divergence theta, we can divide the wavelength by the origin diameter. The amplified photon flux we could measure in the observer plane is about 4.2 times 10 to the 6 photons per meter square per second. Since this is higher than the background flux, we could actually receive their laser message. To conclude, let's look at some of the most Earth-like exoplanets in an overview. The x-axis indicates their angular size and the y-axis indicates their amplified photon flux. We see that the amplified photon flux for all of them is larger than the background brightness. So solar gravitational lensing actually provides a way to find out more about those Earth-like exoplanets. Currently, the NASA Innovative Advanced Concepts program studies the possibilities and the feasibility of a solar gravitational lens mission. So maybe we will soon be able to image an Earth-like exoplanet. For further information, check out the links below of NASA studies on solar gravitational lensing and of my bachelor thesis on wave optics of solar gravity lens. Thanks for watching.